László, the floor is yours.
Thank you so much. Good afternoon, everyone. In the next 10 minutes, I would like to talk to you about quantum communication. Why do we need quantum communication? And why do we need satellite-based quantum communication? The quest we are looking for is about the security, about the long-term security. As you might be aware of, today's encryptions might be attacked by the quantum computers. We have heard a lot about quantum computers during the opening ceremony in this morning, and I'm pretty sure that we will hear a lot about this technology during the next 1.5 days here in Riga during this event. But the quantum computers can attack the encryption techniques and the certification that we are using right now. Fortunately, the quantum technology offers a really good solutions how we can protect our system using a technique which name is quantum key distribution. How can we exchange secret keys which can be used for symmetrical key-based communication in the future. So if we change our some layers of our communication techniques, then our systems, including our entry into the different net banking system or into our Facebook account, will be safe in the future as well. The security of the quantum key distribution is based on quantum physics, on the laws of the quantum physics, and it's compatible with the nowadays used symmetrical cryptography algorithms and system. And there are different types of QKD, quantum key distribution systems. Either they could be prepare and measure based, or they could be based really interesting phenomenon named entanglement. But anyway, they can enhance the security of our system. We know that since the middle of the 80s, when the first QKD protocol has been published in theory. In the past 30 years, there were novel approaches how can we implement quantum key distribution. And right now, we are talking about the next generation of quantum communication. So the first phase is enhancing the classical communication system with quantum technology. The next phase will be connecting different quantum systems, connecting quantum computers which will be built here in Latvia to other quantum computers all over Europe. Quantum internet can do that connection. However, we have some problem with quantum communication. We are using laser signals, single photons or weak coherent laser signals for the communication. And due to the attenuation, our photons cannot go for long distance over optical fibers. The typical limitation is, depending on the commercial device that you would like to use, is around 60, 80 or 100 kilometers. So there are no chances to connect different quantum systems or QKD devices using only optical fibers, only terrestrial segments. This is why we are looking for space. With using satellites, we will be able to connect different systems which are located on different sides of the different places on the Earth. Of course, there are huge challenges when we would like to implement satellite-based quantum systems, because we are using either a single photon as a carrier or a weak coherent laser pulse. There are many different errors which we need to face. The pointing error, we need to find our satellite since we are not using RF signals. And of course, there is the beam spreading. We will start with a tiny point with the size of a photons in a nanometer environment, and by the end, we need to detect a huge signal with a diameter of 10 centimeters, 20 centimeters, even 1 meter. And of course, if we are talking about satellite-to-ground communication, the scattering through the atmosphere can cause further problems in our systems. So in early years of this year 1000, people were shocked that this is theory only, and we won't be able to build systems, satellite systems. But things changed in 2016 when the world's first quantum communication satellite has been launched by China, and they made successful experiments. They had a LEO satellite. The mass of the satellite is around 500 kilograms. And 3 years later, the National University of Singapore, together with a startup company in Singapore, launched the Spooky 1 satellite. It was launched from the ISS, which is a 3-unit CubeSat. And on board of that satellite, they were able to test different entangled photon sorts, which is a really important ingredient for a satellite-based quantum communication. And 2 years later, something happened finally in Europe. The EuroQCI, the Declaration on the European Quantum Communication Infrastructure, was born. It started in 2019. I'm really proud that Hungary joined that summer to this initiative, and 2 years later, by the way, Latvia joined as well. So right now, all of the 27 EU member states are members of the EuroQCI initiative, which will connect the EU member states using terrestrial segments and satellites. The first European quantum communication satellite, which is built by ESA, the European Space Agency, will be the Eagle 1, and it's planned to be launched by the end of the next year, and it's built by an international consortium led by CES, a company based in Luxembourg. So this will be hopefully the first European quantum communication satellite 8 years after China has launched its first satellite. In Hungary, we would like to contribute to the European satellite-based efforts, and we started different national programs. Our first national program was focusing on different aspects of quantum technology, including quantum communication. And the second one is focusing on quantum computing and quantum communication. And of course, we are a member of the EuroQCI initiative as well. With my group, at the Budapest University of Technology and Economics, where I came from, we developed different quantum key distribution devices. They are either fiber-based or free space. And I would like to show you some photos of our free space experiment on which we are currently working. Even the photon source that we are using is made by my colleagues at the university. It was created at the Department of Physics at the university. The detectors have been developed by a Hungarian spin-off company of the university, and we were able to send photons over the river Danube, over our river, with collaboration of Vodafone Hungary, which was member of the Vodafone group at that time. We were able to cover 700 meters of this distance, and the whole system, software and hardware included, have been developed by my colleagues at the university. So right now we are testing how free space QKD can work, and of course we are focusing on the satellite regime. How can someone work in the quantum industry? I believe that we need good people for that, trained people for that. This is why 3 years ago in Hungary, we started to work on our space engineering master program, which was launched last September. This is the very first space engineering master program in my country, launched by the Budapest University of Technology and Economics. And last month, we launched a special training program for computer engineers interested in quantum computing and quantum communication. And since we are a small country, with 10 million people, but with more than 20 universities. We decided to combine our strengths and competencies, and the Unispace education program has been born. Right now in the Unispace program we have 17 universities who are collaborating to educating different people who are interested in the space, either in space technology or in space policy, in space economy, or even at the medical sciences. So this was just a short introduction about what quantum communication can do with space. Thank you very much for your attention.
Thank you, László. Very good presentation. I think the communications is definitely one of the areas where we will need more of it to communicate between planets. So thank you again, László.
Thank you.
So